Hi, my name is Allison Lee, and I'll be presenting my final internship project at Pivotport Inc. for the summer of 2024. My project is on the comparison between classical and quantum machine learning results in portfolio optimization. A very special thanks to Rajiv Mistry and Jonathan Ortega, my supervisors, for all their help with this project. Here's a brief overview about what my presentation will go through. First, I'll present my dataset and the methodology that I used. Then I'll move on to explain the process of training the data and testing the data. After that, I'll speak a little bit about the modifications that I made to improve accuracy. I'll explain the comparison between the original result and the new results. After that, I'll explain the challenges that I went through when working on this project, and then I'll end with conclusions and next steps. As an introduction to my project, my overarching goal was to implement quantum algorithms to perform portfolio optimization for improved accuracy. I decided to perform portfolio optimization on a Dow Jones dataset. The requirements included a robust dataset, classical machine learning, quantum algorithm tools, Qiskit, and a quantum provider. The solution architecture was to compare classical and quantum results using the IonQ provider. The execution plan included pre-processing, cleaning data, training data, optimization, testing data, and analyzing the results. I decided to use the Dow Jones 30 Index dataset. For this dataset, the stock value was collected daily for 17 features, with one of the features being DJIA. There were 5,790 data points for each feature, which gives us a total of more than 98,000 snapshots in time. I created a new data frame that contained just the required columns for this experiment. To be more specific, some data was consistently missing for one of the features, and the DJIA was an overarching measurement instead of a single ticker. For this reason, to ensure accuracy in results, I decided to only use the features that contained accurate data relevant to my goal, so 15 out of the 17 features. You can see listed here the features of the original dataset. For the new data frame that I created, I dropped Walmart because it was missing a lot of values, and DJIA because it was an overarching measurement instead of a single ticker. Another modification that I made to my data frame was to constrain the data to pre-COVID-19. The original dataset included information and data points up till March 31st of 2022, but I constrained my data to only go up till March 29th, 2019. As you can see in the presentation, my training data runs from April 1st, 1999 to March 31st, 2016, and my testing data runs from April 1st, 2016 to March 29th, 2019. Here's how I implemented my methodology. First, I pre-processed and cleaned the data. After that, I connected to the IonQ quantum provider. I then trained the data using classical, sampling SVQE, and QAOA algorithms. After that, I tested the classical and quantum results and reported those results via portfolio value and cumulative return. I then increased the maximum iterations in attempts to improve accuracy. After that, I compared the classical and quantum results for 250 versus 500 iterations. Let's move on to explore the results that I got from training the data. Here, you can see the result of training the data using a classical approach, which is to minimize the eigenvectors. In the image below, you can see the list of tickers that were selected for the optimal portfolio using this classical approach. In this slide, you can see the optimal portfolio selection of tickers for the quantum approach of sampling SVQE. At the bottom image, you can see the list of tickers that were selected for this approach. Finally, we have our optimal portfolio result from the QAOA quantum approach. Similar to the previous slides, you can see the optimal selection of tickers that the QAOA resulted in at the bottom image. Now that we've looked at the results from training the data in both the classical and quantum approach, let's move on to exploring how I tested the data and the analysis that followed from that. In this diagram, I graphed the portfolio value for each of the classical, SVQE, and QAOA's optimal portfolios that was determined in the training data stage. One important thing to note is that I set the max iterations to be 250 with 3 repetitions for each the SVQE and the QAOA when training the data. When we're examining the results here, we can see that SVQE, QAOA, and classical all generally have a very similar graph shape, but we can see that SVQE has the highest portfolio value with QAOA at a close second, and then classical with the lowest portfolio value. This diagram shows the cumulative returns for each the classical, the SVQE, and the QAOA portfolio selections. Something that I found really interesting was that even though in the previous slide, when we were graphing portfolio values, we saw that classical had the lowest portfolio value in general, we can actually see in this specific graph that through the cumulative returns, the overall percentage growth was the highest for classical, and then SVQE, and then QAOA. I found my test results extremely interesting to the point where I wanted to dive deeper and ask myself the question, how can we increase the accuracy of our test results? A possible solution and a hypothesis that I wanted to test out was to observe what would happen if the maximum iteration was raised from 250 to 500. So what I did was I retrained my data with 500 iterations instead of 250. Here we can compare the selected tickers for classical, sampling VQE, and QAOA's optimal portfolios when we went from 250 iterations to 500 iterations. One important point to notice is that the classical tickers remain the same throughout the change in iteration. And the reason for this is because a change in iteration is only applicable to the quantum algorithms, not the classical ones. So for that reason, we can see here that classical tickers has remained the same as it should have. However, one thing that changed is that the sampling VQE tickers and the QAOA tickers have altered as we went from a 250 iteration to a 500 iteration. Now we can compare the portfolio values between the 250 iterations and the 500 iterations. We can see that SVQE and classical maintained its general shape as we increased the maximum number of iterations to 500. But with QAOA, it seems to have a much larger portfolio value increase towards the end of the dataset when we have a 500 iteration. Additionally, unlike the 250 iterations, when we have 500 iterations, there's a crossover between the SVQE and the QAOA at around May of 2017. We're following from that point, the SVQE and QAOA start to diverge. I evaluate that the reason why the QAOA increases portfolio value for the 500 iteration is because after more iterations, the QAOA is able to find a more optimal portfolio selection that gives us a higher portfolio value. Yet we also have to be aware that the QAOA algorithm is exposed to the penalty mechanism, which is a cost component of the Hamiltonian. Therefore, it's important to note this limitation when analyzing the QAOA result, because with our current resources, quantum algorithms are much more error-prone compared to classical algorithms. Now we can go ahead and compare the cumulative returns for the 250 iteration and the 500 iteration. For the 250 iteration, we can see that there's a slight crossover and overlapping between the SVQE and QAOA. But in general, the shape and the overall level of cumulative returns are pretty similar. On the other hand, for the 500 iteration model, we can see that there is much less variance between the SVQE and classical, which shows that as the iteration increases, the cumulative return of SVQE becomes more similar to that of the classical. Something else to notice is that for the 500 iteration model, there's a crossover between QAOA and SVQE at around September of 2016. And after that point, they continue to diverge so that the cumulative return for QAOA near the end of the dataset is much higher than that of SVQE. This increase in QAOA cumulative return actually supports the graph in the previous slide, where we observed that the QAOA was able to find a more optimal portfolio selection in the 500 iteration that gave us a higher portfolio value than that of the 250 iteration. In our current graph shown here, we can see that the percentage return is much higher in the 500 iteration than the 250 iteration, especially near the end of the dataset. Therefore, we can conclude that the increase of iteration from 250 to 500 resulted in more accurate results, where the selection of tickers gives us an optimal portfolio that leads to a higher portfolio value while taking into account the risk, budget, and other constraints. A challenge that I faced when working on this project was the time constraint. This idea and exploration is a much larger topic than can be covered in a single presentation or a single project, and is something that needs to be continuously researched over time. But I had less than a month to work on the project, which I believe really constrained the depth of my research and project. For example, I was initially interested in exploring and comparing the execution times between the classical algorithms and the quantum algorithms, as well as the accuracy. But I realized as I was researching that it's not simply just timing how long it takes to run the code for each the quantum and the classical, but it's actually more about the quantum time series and how that compares to the classical time series. It required a lot more field knowledge and research and more time and resources than I had to work on the project, which is why I believe time constraint was one of my biggest challenges. As a conclusion, I started off this project wanting to explore the accuracy and execution times between classical and quantum algorithms. And I think at this point in time, we can conclude that the quantum algorithm is much more error-prone and slower than the classical algorithm. However, with more advanced quantum resources, hardware, and error correction, the quantum method would definitely result in more accurate and faster results. More time and more advanced computational resources would allow us to fully harness the potential of our quantum algorithms and network. In terms of next steps, something I would like to continue to research about is the QAOA and SVQE theory, especially exploring the penalty mechanism of the Hamiltonian to determine more deeply the cost of increasing iterations for both the QAOA and SVQE. I would also like to learn more about how to apply a quantum error correction technique to decrease error levels in quantum tools from quantum noise or other factors. Thank you for listening.